Okay, in this video I'm going to be talking about the idea of uniform circular motion, which is an important case of two-dimensional motion. Uniform circular motion is defined as motion in a circular path at a constant speed. And you could probably think most easily about maybe a car that's driving on a circular track, and the car is driving in a circle and maybe has the cruise control set so that its speed never changes. So, it would be something like if you were looking at the car from overhead, you would have the car here, and I'm going to try to draw a circle to show the car's path. And so the car might be driving, driving to the right when you take the picture, and then as time goes on, the car basically drives around, and its velocity is going to change directions because velocity is a vector, and its direction is going to be changing all the time. So that's kind of what happens with uniform circular motion. And the constraint that we're going to put on this is that the speed of the car doesn't change because its cruise control might be set. So the velocity of the car is actually changing, and that's because the direction is changing of the velocity. But the speed itself doesn't change, and sometimes that's a little bit confusing to students because they think that velocity and speed are the same thing, and they're not really, because velocity has a direction component. So let's think about a car that's doing this, that's moving in a circle at the same speed but with a changing direction. And you could imagine the circle might have some radius r. What I'm going to do is kind of show you that in a case like this, that there's a special type of acceleration that happens. And the acceleration is called centripetal acceleration. And that acceleration is going to be directed towards the center of the circle at all times. And so these vectors that I'm drawing here are actually acceleration vectors, and they always point towards the center of the circle. So this A that we're talking about is called centripetal acceleration. Now, if you think back to some of the things that we talked about, we've talked about cases where when the velocity vector and the acceleration vector, tend to line up, that corresponds to an object which is maybe increasing its speed. So for example, if the acceleration vector goes this way and the velocity vector goes that way, that's going to be, speeding up. If the situation is different and the acceleration and velocity are in opposite directions, of course that's slowing down. And then the question would be, well, what happens if the acceleration and velocity vectors are at a right angle to each other, perpendicular, like they are up here? And that's going to result in cases where you have turns, or turning. Okay? So that could be like this and that. And in this case, what's going to happen is the object is actually going to begin to turn in the direction of the acceleration. Okay. If the acceleration vector makes kind of a right angle to the velocity, then that's the only thing that's going to happen, is that the object will turn, and its velocity is not going to increase or decrease because the acceleration doesn't have any component along its direction. So in this video, what I'm going to do is first of all, lay out that argument that centripetal acceleration is perpendicular to velocity, so you won't have any change in speed. And I'm also going to derive a pretty famous formula for centripetal acceleration, which states that centripetal acceleration is equal to the velocity of the object squared divided by the radius of its circular path. So in terms of coming up with this formula, I'd like you to find your sheet that has some of these diagrams on it. This is actually from your textbook. And what we're going to do is just show kind of through geometry where the centripetal acceleration formula comes from. All right, so first off, we're going to want to give a special name to the velocity of an object moving in a circle. We're going to call this the tangential velocity. So v is called tangential velocity because the vector that represents that velocity is really tangent to the circle. So that velocity can be, you can find its magnitude, how big it is, how fast the object is moving, by taking the circumference of the circle and dividing by the period, the time it takes for the object to drive around it. Okay, so this is your circumference. So that's a distance. Hope you recognize that. And t is the period. The period is the time it takes to go around once. So circumference would be measured in meters. The period is in seconds. Your velocity is going to be in meters per second. Okay. All right. So here we have this tangential velocity vector drawn for one instant of time. So now let's imagine what happens if you pick two different instants of time. All right, these are labeled as points P1 and P2 in this figure. So between the 2 points, there's going to be a change in velocity. V1 and V2 are labeled right here and right here. And those would be the velocities of the object at those two different times. But notice that those are tangent to the circle. And because we're talking about uniform circular motion, they have the exact same length. Okay. So what we're going to do is we want to say, well, if that's happening, if that tangent is turning, then there must be some type of a change in velocity that we can calculate. Okay. So what we're going to do is we're going to come back to, we want to find an acceleration here. And we want to use the definition of acceleration, which is it's a change in velocity over time. This is kind of strange because you're probably thinking, well, I thought we said there was no change in the object's speed, so how is this going to work? And this is kind of where the magic of vectors comes in, because you can actually, there is a change in velocity that you can use in this formula, and that's going to give us the formula that we're looking for at the end of the day. So let's see if we can come up with this. What we're going to want to do is to basically come up with, a way of writing down the change in velocity using our vector picture that's over on the left. So this is the tricky part. What we're going to do here is, first of all, take a look at this triangle that we have here. Okay, I'll kind of shade it in like that, and that's a isosceles triangle, right? Because the radius makes up the two sides, and then over here on the opposite side, you have what's called delta S. And delta S is an arc length. But if you make this triangle really skinny and make a very small wedge out of it, then delta S is really almost like a straight line. And that's kind of the key idea here, is that delta S, which is strictly speaking an arc length, we're going to say that it can be approximately a straight line because we're taking a very narrow wedge here. Okay. All right, so how does that help us? Well, take a look at the picture underneath it. All right, this is going to be an example of vector subtraction. All right, well, what does this mean? Well, if you take V1 and V2, I'll circle those, and you subtract them, you are going to get a change in velocity, which is given by this vector right here. Okay, that may not be easy to see at first, but remember that a change in velocity is equal to V2 minus V1. And we're talking about vectors here. Okay. So if I were to sketch V2 like so, and then I were to subtract V1, that's a head to tail sort of a thing. It's like adding negative V1. And the resultant that I get is going to be my change in velocity. Okay, there it is. And that vector is the same vector that I circled up here. I just kind of showed a different way of getting it. So notice that that vector points towards the center of the circle. That's really important. If you were to take this vector and put it up in this picture, it would look like that. It would be pointing towards the center of the circle. And that you might have to ponder that a little bit to really buy into it, but it actually does. So if you were to take this triangle and kind of turn it around by 180 degrees, it would look like the picture here. This triangle is actually similar to the original one that I sketched. Okay, and that's how we are going to get our expression for delta V that we need to put into this equation. Okay, so here's the relationship that you get out of this. If you look at the top triangle, you have the ratio of, if you take the delta S divided by the radius of that triangle, okay, that gives you a ratio from that triangle. If you look at the bottom triangle, basically the same ratio could be obtained by taking a change in velocity and dividing it by the velocity, the tangential velocity itself, either v1 or v2, it doesn't matter, because it's just the magnitude here. And this is the key thing, okay? So this is going to help us a lot. So we're looking at similar triangles and we're kind of coming up with a ratio. And remember, what we're going after is this delta V. So if you rearrange for that, you get delta V is equal to V times arc length over R. That's going to be what I put in up here. Okay, and I divide that by time. And then I'm just going to simplify this, and I'm going to have V over R. Pull that out, times delta S over T. Okay. And so that's going to be what our expression is for the average acceleration from point 1 to point 2. Now, what we're really interested in doing is taking that average and shrinking it down and going for a really, really skinny triangle. So we want an instantaneous acceleration. And of course, you can find that by taking the limit as delta V over T as T goes to 0. Okay? So we're going to take the limit of the average acceleration and the limit as T approaches 0. This is how you find the instantaneous anything. And so if you do that, you're going to take, I'm going to copy down my expression, V over R. And then you're looking at what's left. I have arc length, delta S over T. You might be thinking, well, T is going to 0, that makes this 0. But in fact, this is actually approaching V. Okay? This is kind of like going from average velocity to instantaneous velocity. So this doesn't blow up. This actually becomes the tangential velocity. And that gives you V. So what we end up with is V times V divided by R. That's V squared over R. Okay. And that's the famous formula for centripetal acceleration that I was talking about at the beginning. It actually has a number value. So if you know how fast an object is moving, what its tangential speed is, you can square it and divide by the radius. And that will give you an acceleration in meters per second squared, which is basically the acceleration which makes you turn in a circle. That acceleration does not make you go faster or slower. All it does is it turns you. That's it. Okay. And then typically in problems, if you want to find that velocity, you go back up here, and you have to find the velocity usually by knowing the radius and the period and working with that. Okay. So that's kind of the idea of that. Down on the bottom here, there are a couple figures that I took from the book as well to show what uniform circular motion would look like if you could see the vectors at different points. So this picture is very much like the one that I began with when I did the sketch of the car driving in the circle. Okay, so that, in other words, the acceleration is always perpendicular to the velocity. Okay, so that's something we should recognize. We'll come over to this other case. This is something that you can read about in the chapter, but they talk about what if the motion isn't uniform? What if something is swinging around in a circle like a bucket at the end of a rope? In that case, it gives you a little bit more to think about because the velocity actually changes as you go through the different points of motion. And I think that's probably something that we could best discuss in class together. But it gets a little more complicated because that motion is non-uniform, because gravity is causing you to slow down in one direction and speed up in the other. Okay? So the main point here is that we've kind of defined what uniform circular motion is, and we've come up with a way to find the value of the tangential velocity of the object, and we know how to figure out its centripetal acceleration, and we have a formula which is going to be very useful for us in the future for finding centripetal acceleration. Okay.